Welcome to the 8th session of this circular function series. In this session, we will show how trigonometry relations can be used to transform one form of expression to another. We will present questions related to trigonometry and logarithmic-based composite functions, and show how to use the properties of trigonometry functions along with algebra skills to solve various problems. We will demonstrate and explain in details through 10 worked examples in this session.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the 8th session of this circular function series. Here, example 1 is to prove the relation of x plus its reciprocal equals 2 secant theta, given that x equals secant theta minus tangent theta, and hence to express x minus its reciprocal in terms of theta. Since x equals secant theta minus tangent theta, its reciprocal equals 1 over the result of secant theta minus tangent theta. After multiplying its conjugate on both numerator and denominator, 1 over x equals secant theta plus tangent theta. Hence, x plus its reciprocal equals secant theta minus tangent theta plus secant theta plus tangent theta, which equals 2 secant theta as required. Accordingly, x minus its reciprocal equals secant theta minus tangent theta minus secant theta minus tangent theta, which equals negative 2 tangent theta.
There are 4 trigonometry relations to prove in example 2, and let's do it one at a time. To prove these relations, we need to apply various trigonometry identities. As for question A, the two complete squares are expanded and both of the middle terms are just cancelled. According to the Pythagorean identity, the left side equals 2 sine squared x plus 2 cosine squared x, which equals 2, and this exactly matches the number on the right side. As for question B, after applying the reciprocal identities on secant squared theta and cosecant squared theta on the left side of the equation, the numerator is replaced by sine squared theta plus cosine squared theta. Hence, the left side equals the reciprocal of cosine squared theta plus the reciprocal of sine squared theta, which is secant squared theta plus cosecant squared theta as required. As for question C, the left side of the equation is factorized using the formula of the difference of two squares. After being factorized, the left side equals sine squared x plus cosine squared x, or in parentheses times sine squared x minus cosine squared x, or in parentheses. After being further factorized, the result of sine x plus cosine x, or in parentheses times sine x minus cosine x, or in parentheses, are obtained, which matches the expression on the right side. As for the last question, the expression on the left side is initially transformed using quotient and reciprocal identities. After combining them into one fraction, it becomes cosine x minus 1, or in parentheses squared over sine squared x, which is further arranged to 1 minus cosine x, or in parentheses squared over 1 minus cosine squared x. The details of further simplification can be seen on the screen. We divided both numerator and denominator by cosine x, and then the left side equals the ratio of secant x minus 1, or to
to the sum of secant x plus 1, which is the expression of the right side. Based on the relation provided in example 3, sin theta plus cosine theta equals 3 over 5. The question in this example is to evaluate two trigonometry expressions. Since sin theta plus cosine theta equals 3 over 5, both sides of the equation are squared. Hence, as for the first question, 1 plus 2 sin theta cosine theta equals 9 over 25. So sin theta cosine theta equals negative 8 over 25. As for the second question, sin cubed theta plus cosine cubed theta can be factorized using the formula of the sum of two cubes. After being factorized and simplified using the Pythagorean identity, sin cubed theta plus cosine cubed theta equals sin theta plus cosine theta, or in parentheses times 1 minus sin theta cosine theta, or in parentheses, which equals 99 over 125. Example 4 is to evaluate a trigonometry expression which can be simplified using supplementary and complementary relations. Hence, we have negative pi over 6 minus cotangent 47 degrees times negative tangent 47 degrees times tangent 45 degrees, which equals 1 minus square root 3 over 2 after being simplified. Example 5 is to find the value or values of m given that sin theta equals m minus 3 or over the sum of m and 5, cosine theta equals 4 minus 2m or over the sum of m and 5. According to the given criteria, we may apply the Pythagorean identity relation to establish an equation with m as its parameter. Hence, we have m minus 3 or over the sum of m and 5, or in parentheses squared, plus m minus 3 or over the sum of m and 5, or in parentheses squared, equals 1. Since both fractions have the same denominator, the equation can be simplified by combining the two fractions into one. Hence, the quadratic equation can be solved using quadratic technique, and the results of m are then obtained. So we have m sub 1 equals 0 and m sub 2 equals 8 accordingly. Example 6 is to evaluate a composite function logarithm base cosecant squared theta of the ratio sin 2 theta to 2, given that logarithm base tangent theta of cosine theta equals 2 over 3 and theta is between 0 and pi over 2. Since theta is between 0 and pi over 2 and logarithm base tangent theta of cosine theta equals 2 over 3, logarithm base cosine theta of tangent theta equals 3 over 2. So logarithm base cosine theta of sin theta over cosine theta equals logarithm base cosine theta of sin theta minus logarithm base cosine theta of cosine theta equals 3 over 2. Hence, logarithm base cosine theta of sin theta equals 5 over 2. Now let's come back to the composite function we're going to evaluate. Since logarithm base cosecant squared theta of sin 2 theta over 2 equals logarithm base cosecant squared theta of sin theta plus logarithm base cosecant squared theta of cosine theta, which can be expressed to the reciprocal of logarithm base sin theta of cosecant squared theta plus the reciprocal of logarithm base cosine theta of cosecant squared theta. Further simplification enables us to find the expression that equals negative half minus the reciprocal of 2 logarithm base cosine theta of sin theta, which equals negative 7 over 10.
The questions in example 7 are based on the quadratic equation of 2x squared minus square root 3 plus 1, or in parentheses times x plus m equals 0, where sine theta and cosine theta are the two roots of this equation. The angle theta is located in the first quadrant. The first question is to simplify the trigonometry expression, the ratio of sine theta to the result of 1 minus cotangent theta, plus the ratio of cosine theta to the result of 1 minus tangent theta. According to the quadratic Vieta theorem, sine theta plus cosine theta equals the sum of square root 3 and 1 all over 2, and sine theta cosine theta equals m over 2. As for the first question, the expression can be simplified by multiplying sine theta on both numerator and denominator of the first term, and multiply cosine theta on both numerator and denominator of the second term. After simplification, the expression is simplified to sine theta plus cosine theta, which equals square root 3 plus 1 all over 2. As for the second question, based on the Pythagorean identity relation, sine theta plus cosine theta, or in parentheses squared, equals 1 plus 2 sine theta cosine theta, which equals square root 3 plus 1 all over 2, or in parentheses squared. Hence, the value of m, which equals 2 sine theta cosine theta, is calculated, and it equals square root 3 over 2. Here we continue to work on question 3 of example 7. Since 2x squared minus square root 3 plus 1, or in parentheses times x plus m equals 0, its discriminant equals square root 3 plus 1, or in parentheses squared, minus 4 times 2 times square root 3 over 2, which is simplified to square root 3 minus 1, or in parentheses squared. Hence, x sub 1 equals square root 3 over 2, and x sub 2 equals 1 over 2. Since 2 sine theta cosine theta equals square root 3 over 2, sine 2 theta equals square root 3 over 2. Since the angle theta is between 0 and pi over 2, 2 theta equals arcsine of square root 3 over 2. Based on that, we calculate the angle theta equals pi over 6. So the two roots and the angle theta are square root 3 over 2, 1 over 2, and pi over 6. Example 8 is to evaluate the trigonometry expression of 1 minus tangent alpha, or over the sum of 1 and tangent alpha, given that sine alpha plus cosine alpha equals 7 over 13, and alpha is between 0 and pi. After careful observing the expression in terms of the tangent function, we find that if we multiply cosine alpha on both numerator and denominator, it becomes cosine alpha minus sine alpha, or over the sum of cosine alpha and sine alpha. So, we need to find the values of both sine alpha minus cosine alpha and cosine alpha plus sine alpha first. Now, let's start to work on that. Since sine alpha plus cosine alpha equals 7 over 13, after both sides of the equation being squared and arranged, 2 sine alpha cosine alpha equals negative 120 over 169. Due to the angle alpha is between 0 and pi, and the sine alpha cosine alpha is less than 0. Therefore, the angle alpha is located in the second quadrant, which implies that cosine alpha minus sine alpha is less than 0. Hence, 1 minus 2 sine alpha cosine alpha, which is cosine alpha minus sine alpha, or in parentheses squared, equals 289 over 160.
So cosine alpha minus sine alpha equals negative 17 over 13, and thus the original expression equals cosine alpha minus sine alpha, all over the sum of cosine alpha and sine alpha, which equals negative 17 over 7. Example 9 is to find the implied domain for the function fx, which equals natural logarithm of cosine 2x minus pi over 3 over the result of tangent x minus 1. Based on the property of logarithm, cosine, and tangent functions, we establish the inequalities that cosine 2x minus pi over 3 is greater than 0 and tangent x minus 1 is not equal to 0. Since cosine function is greater than 0 when 2x minus pi over 3 is in the first and fourth quadrant, then x is between n pi minus 7 pi over 12 and n pi plus 5 pi over 12. Since tangent x minus 1 is not equal to 0, then x is not equal to n pi plus pi over 4. After intersecting both inequalities, the implied domain is the set from n pi minus 7 pi over 12 to n pi plus 5 pi over 12 except n pi plus pi over 4, where n is an integer. Example 10 is to find the period of the function fx, which equals sine to the fourth of x plus cosine to the fourth of x. To find the period of fx, we need to simplify the function first. Since the function is expressed in sine and cosine functions, Pythagorean identity relation is used here to simplify the function. Therefore, sine to the fourth of x plus cosine to the fourth of x equals sine squared x plus cosine squared x, or in parentheses squared, minus 2 sine squared x cosine squared x, as seen on the screen. The function is then simplified to 1 minus half times sine squared to x. Since sine squared to x can be written to 1 minus cosine 4x all over 2, according to the cosine double angle formula. Fx is then simplified to 1 over 4 multiplies cosine 4x plus 3 over 4. Hence, the period of function fx equals 2 pi over 4, which is pi over 2. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.